This conference will now be recorded.
प्रसन्नवदनं ध्यायेत् सर्वविघ्नोपशान्तये अगजा आननपद्मार्कं गजाननमहर्निशम् अनेकदन्तं एकदन्तमुपास्महे एकदन्तम् या भुक्ते तुषारहारधवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना या ब्रह्माच्युतशङ्कर प्रभृतिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती Charya हस्ते स्फाटिकमालिका विदधति पद्मासने संस्थिता वन्दे तां परमेश्वरीं भगवतीं बुद्धिप्रदां शारदाम्।
Hello everyone, welcome to today's webinar. Now, I would like to play a speech from the Honorable Principal Sir, Dr. A.K. Sharma.
Today webinar, I acknowledge to Federal Department of Language and the winner, Professor S.K. Srivastava and coordinator Dr. Somakti and the entire organizing team and wish them good luck.
Now I would like to invite our head of the department, Honorable Professor S.K. Srivastava, to please come and welcome everyone.
Hello everyone, are you hearing? Respected Principal Dr. A.K. Sharma, Coordinator TK3 Dr. Rajiv Chandak, experts of today's webinar Dr. Shantanu Majumdar and all the dear participants. It gives me great pleasure to extend a warm welcome to all of you participating in this one-day national webinar on water quality assessment, a modern chemical approach. This is a topic of everybody concerns. I am sure that you all will feel enriched with knowledge and new ideas of Dr. Shantanu Majumdar after the completion of this event. I welcome you all once again
Unmuted.
this national webinar. Now I request Dr. Sovik to introduce today's expert, Dr. Shantanu Majumdar. Thank you.
Thank you, HOD sir, and the convener for today's event. So, good afternoon, my dear friends, colleagues, and students. I welcome you all on sorry for the interruption. So, good afternoon, my dear friends, colleagues, and students. I welcome you all on today's national webinar on chemical approach. On behalf of the organizing committee, it's my pleasure to introduce our distinguished speaker, Dr. Santanu Majumdar. Dr. Majumdar is currently a Fulbright Nehru Fellow at Texas A&M University, USA, and an expert water consultant at Saki Waters. Dr. Majumdar completed both his bachelor's and master's from University of Kalyani, West Bengal, India. Dr. Majumdar completed his PhD from University of Girona, Spain, in analytical chemistry in 2013. Upon completion of his PhD, Dr. Majumdar served as a full-time faculty member at the Department of Ecological Engineering and Environmental Management at University of Kalyani until 2016, before moving to Texas A&M University, USA. In addition to Fulbright Fellowship, Dr. Majumdar received several other prestigious fellowships, including Gian Maria Giuppi Scholarship from University of Venice, Italy, Erasmus Mundus Doctoral Scholarship from European Union, and Dan Doctoral Scholarship from Germany. Dr. Majumdar research interests are analytical method developments, environmental analytical chemistry, trace and heavy metal contamination. Dr. Majumdar has authored a book chapter and published several research articles in high-impact peer-reviewed journals, including Water Research, Journal of Hazardous Materials, and Science of Total Environment. Dr. Majumdar has delivered several invited lectures around the globe and holds membership of several prestigious international societies. In addition to his illustrious academic career, like many other born and brought up in West Bengal, Dr. Majumdar is very passionate about football and quite vocal about the socio-economical issues and injustice over several social media platforms. Let's welcome once again today's speaker, Dr. Santanu Majumdar. However, before I hand the session or platform over to Dr. Majumdar, a small announcement. We'll be accepting questions throughout the talk. Please write your questions in the chat box with your name and affiliating institute. I also request you to keep your microphone muted during the session. We won't email the feedback form, but share the link for the feedback form in the chat box in the meeting app. So look forward to it. So yeah, that's it from my side. Over to you, Dr. Majumdar. We are looking forward to your talk. Thank you. Thank you very much.
Thank you, Dr. Shobhit. I hope I am audible to all the participants. I hope so. So, if I do, then let me just open my presentation first.
You are audible, but you have to open your camera too.
Okay, and is my screen visible now?
Not yet, but yeah, I can see your presentation, but I cannot see you. Please open your camera too.
So, do I need to first like show myself and before the presentation?
It will be better if.
Okay, I'll do that then. Okay, I'll do that. Just a moment in that case.
Thank you.
Okay, so I tried, but I don't know, it says due to some technical difficulties, they can't show, like my camera is not visible, I don't know. I mean, it's showing that it's on, but I don't know if you can see me.
No, we cannot see you.
And now?
No, sir.
Okay, so, yeah,
Yeah.
I don't know why, but it's coming on and going off.
Okay. Maybe the internet connection is slow, sir. You can start with the presentation then.
Okay. Good afternoon, everyone. Okay, that's great. Okay, so I don't know the camera, maybe it's not working. So, good afternoon again, everyone. My name is Dr. Shantanu Majumdar, and I guess Dr. Dey had already explained most of the things that should be talked about my background. So yeah, I mean, I am basically an environmental analytical chemist. My major interest is to bring chemistry from the lab and then apply it for the environmental issues of concern. So that's in nutshell. And it's an honor, and I'm really thankful to Jawahar Engineering College for giving me this opportunity to talk about my research and research interest. Before I start my presentation, I would like to say that this work is basically a decade-long story. The story that everyone should know if anybody is interested in water research, specifically related to the arsenic contamination of groundwater, because that's one of the most important and major concern across the globe right now. Okay, so let me is my screen feasible now?
Yes, Dr. Majumdar.
Okay, great. Okay, so let's start. So as you can see that I'm going to talk about the different pollution aspects of arsenic in natural water, specifically groundwater in this case, chemistry, and how we can remediate this problem, and a bit of its analytical advances. Well, in fact, it's the most important part that I'm going to talk about. So, as you guys are from the Department of Applied Chemistry, I thought that this would be the most relevant thing to talk about when you can apply chemical knowledge to solve or resolve environmental issues. That is a matter of concern right now. So, before I start, let me give you a glimpse on what I do exactly. So, as I said, I'm an environmental analytical chemist. I like to go to the field where the problem exists. I like to collect my own samples, be it water, sediment, or anything else, and I'd like to bring them in the lab, analyze them, and most interestingly, I would like to develop my own analytical method, maybe more greener one, or maybe more cheaper one, or more user-friendly one, whatever it may be, depending on the necessity and situation. So I really like to develop my own analytical methods. So going to the field is another thing that I really like, because you get to go to very interesting places that you don't normally get the chance to. So, and some of them are, like, apart from being interesting, could be dangerous too. For example, this one I can see, it says it was a salt march near a coastline in the intersection between Texas and Mexico. And every 4 meters you can get to experience one rattlesnake. So, imagine you're collecting your samples, half drowned in the salt marsh, and then you can see snakes moving around all around you. So yeah, but I love it. Okay, so that's what I do in a nutshell. So there are 2 different study sites that I have walked till now. Actually 3, but these 2 that I'm going to talk about, show you now, is the most important one. One is called the Sargent site, which is near the Matagorda Bay in the, near Mexico, as I just show you in the previous slide, the salt marsh area. Another site which I am going to focus today during my talk is in West Bengal, as you can see. So in West Bengal, you have a district called Nodia, which is on the eastern side of the state, nearing the Bangladesh border. And within the Nodia district, there is a block called Chagda block. That is my study area. And this Chagda block is actually very, very well known in terms of arsenic contamination in groundwater. Well, actually, the entire Nodia district is highly contaminated with arsenic. But my focus area for today's talk would be the Chagda block. So this is the one. And I come from pretty much somewhere near here, but don't worry, I am not contaminated with groundwater arsenic yet. But anyways, yeah. So as you can see, it's located around the river Hooghly. This meandering belt right here is actually the river Hooghly, or you can say the part of river Ganges. So on the eastern side of it, if you go east, you may reach Bangladesh in one hour of drive, and on the west, it's the different states of West Bengal and the mainland India, of course. So that's my study area, and I'm going to talk. My talk will be focused on this particular site. So my talk would be mostly divided in three parts. One, of course, talking about a bit of arsenic and different water-related issues around it, centered around it, and then I'll talk about the different hydrogeochemical aspects. So it's very important before you handle an issue, you have to understand the background of the problem itself. So it's important to understand the geochemistry and the water chemistry together, how it works and what are the problems we call it. So that is the hydrogeochemical aspect. And then I have merged the remediation part of the removal method and of the analytical method development together into the analytical aspect section. So that's what I'm going to talk about. So let's start and see what arsenic is. Okay. So arsenic was first discovered by Albertus Magnus, like back in the 18th century, and it's a very, very well-known element. I'm sure you all have already known about it. If not, then maybe this COVID crisis has actually introduced you to arsenic, because there was a homeopathic medicine that almost many people were suggesting to tackle the COVID situation for arsenic bovine, which contains a very small dose of the elemental arsenic. And it's not now, but since the Middle Ages, arsenic has been used for different purposes, for cosmetics, for medicines, for preservatives, for many other things. So, arsenic can exist in many different forms in the environment, okay? Principally it is either in form of the inorganic forms, or it's the organic forms. But the organic forms are really, really, very, very less predominant or prevalent, because the concentrations are usually very, very low in the environment. So the major important species that you found that you find in the environment, be it water or anywhere else, is the inorganic arsenics, but specifically in water, in natural waters. And inorganic arsenic is actually divided into two different species. One is the arsenate, which is arsenic +5. That is the oxidation state is +5, and the arsenite, which is the +3. And not only they are the most predominant forms, they are the most toxic ones as well, because of their higher bioavailability and also their mobility in the environment. They move very fast from one compartment of the environment to other. So if it's in water, it can quickly go to, bioaccumulated by the plants, by your rice, by your wheat, whatever you're eating there. If it is in the sediment, then it may get quickly released to the water, and from one particular source of water, it can easily move to the next one, and finally contaminate the entire system. And that's how actually the story has been. So inorganic arsenic is the most toxic ones. Among arsenic and arsenite, arsenic arsenic +5 form generally exists in reducing water. So I'm going to explain what we understand for when we say reducing water. So arsenite, the +3 form exists in the reducing water, and arsenate, the +5 form exists in oxidizing waters. Usually, the study site that we're going to talk about in West Bengal, it's a it's a reducing water system. It's a reducing aquifer. I don't know if if you're familiar with the term aquifer. Aquifer is basically the water reservoir underneath the ground. So in a very very simplistic form, if I want to mention that. So the water reservoir or the aquifer in West Bengal is very very reducing in nature. That's why you get more of arsenite, and arsenite is a very very toxic thing. Because in the periodic table, arsenic was the first natural element to be declared as the carcinogenic element, and it's actually the most carcinogenic element among all the known natural elements till now. So you understand that what's the trait from arsenic that we can get. Now, talking about arsenic, why is it important? Why am I talking about arsenic? Why is it important to have a 2-hour long discussion about it? It's important because in 2000, the World Health Organization has actually declared the arsenic contamination in groundwater as the largest mass poisoning in the world. So what it means is it has actually affected most number of people, millions and millions. The number is almost around 73 million people around the globe. Or they have died. So that's why, and its biomagnification level is really really widespread. So as I said, if it is in your sediment, it can go quickly to your water. From water, it can quickly biomagnify to your crops, your food stuff, starting from wheat, rice, or so. The entire world is actually concerned because of that matter. And the problem is that the manifestation time is really, once you are affected, the manifestation time is really, really long. So you're really, really late before you can, get diagnosed with the arsenic-related health issues. So that's another problem. But the most important problem is there is no specific clinical solution available if once you have an arsenic. There are different, trial and error methods that are going on right now. There are different researches going on right now. But the problem is there is no clinical solution, specific clinical solution available, and there are many suggested removal technologies that are there, but not really one that could be universally applicable. Because the problem is most of the countries that you see here are from the developing nations, being it in Latin America, being it in Asia, being it in Africa. So if you can develop a lot of number of remediation strategies, but if they are really really expensive, then it's a problem for the policymakers from these countries to actually apply them or actually imply them in the real world. Okay, so that's the huge problem. The World Health Organization has actually put the guideline, the drinking water guideline, that is for arsenic is the 10 microgram per liter of water. It sounds very less, but even with that, if you consume for a longer period of time, then you may get various health issues that I'm going to talk about. And not only that, in today's world, researchers are coming out that actually even below this concentration, way below this concentration, arsenic can cause a lot of health issues. Like, for example, in Netherlands, they have already brought this particular guideline down to 3 micrograms per liter. And there are talks about bringing it down to 1 microgram per liter. Now, why is it important? I mean, it sounds like it's easy, right? If you have a remediation strategy, and you can decide, to what concentrations you have to bring down your groundwater concentrations of arsenic. But it's not easy. It's not easy at all. To reach a level of 10 microgram per liter when you have a concentration, for example, in my study area, the highest concentration sometimes I get is around 1,000 micrograms per liter of arsenic. So it's a huge concentrations, and not many remediation strategies are available that could bring it down from 1,000 to 10. Forget 1,000, even if it is 200, they're bringing it down from 200 microgram liters to 10 microgram per liters is not easy at all. Even if you can, in very rare cases, it's highly expensive. And I'm talking about, for example, $100 for per liter of water. Just imagine. If you have to spend $100 to do that for just 1 liter of water, and sometimes to have a very precise remediation Okay, so that's not easy. So that's the problem. As I said, the safer limit is people are talking about 3 to 5 microgram now, and in some cases 1 microgram. Now, what are the health, issues that could cause? So you can have various, health issues based on your different organs or body
Hello?
parts. If you want to have a longer period of arsenic, yeah.
Dr.
I hear
Majumdar,
somebody.
Dr. Majumdar, just sorry to
Yeah.
interrupt you. Could you take little
Right.
bit effort to switch on your camera if possible somehow, because that will make the audience more engaged in your talk
Okay,
when you see
I'll
your
try.
face.
I'll try.
Yeah, please.
Give me a
I'm sorry to
moment.
interrupt you, but that I guess would be
No, it's okay. That's
more
okay. I'm just
engaging
giving
even
it time
for
so
the.
that I can. Because I tried once, it didn't work for some reason. I don't know. I'll try again. I don't know. For some reason, it's not working. I don't know why.
But it
Come
worked
on.
when we tested, so wonderful.
Sorry, doctor, but I don't know if it's not working.
Okay, it's fine. It's absolutely
If I
fine.
should
It's absolutely
wasting
fine.
more time on that.
Absolutely
Yeah,
fine.
okay.
You go
Thank
ahead
you.
with your talk.
Yeah, thanks for understanding. I mean, when the questions come, maybe I would switch on my camera and close the presentation to explain things. Okay. So, okay, back to what I was saying. From your skin to your liver to your cardiovascular system to from your nervous system, everything can be affected once you have once you reach a certain level of arsenic for a longer period of time in your diet, in your water, or whatever it may be. And you can see, so these are the outside manifestation that I have got to see. And this is basically called the skin lesion. So when you see some porous things coming out of your skin at the very beginning. When you have more chronic exposure to the arsenic, it can lead to skin cancer, keratosis, and things like that. And sometimes even amputation of your different body parts is needed to save you from being dead. So that's what it is. The good thing about the organic arsenic is that mostly they get excreted through your urinary system, so that's why they are not that threatening. But the inorganic arsenic is a huge problem because it actually gets it indulges with your biomethylation system inside your body. So it's very difficult to get rid of them once it is inside your body. So that's the problem. So the goal is to somehow stop the arsenic from getting into your body. Your body. That's the goal. Because once it is inside, it's very difficult, at least till now. Okay. Now, talking about arsenic, as I said, the important thing is how is it coming into the system? We all know that there are different arsenic bearing or arsenic minerals in the sediment in the environment. But the thing is that how is it coming into the water? That's very, very important thing to understand. So there are different mechanisms that have been suggested till
Dr. Majumdar? হ্যাঁ, ওটাকে তোমার কি তুমি কি হয়ে গেছো, ডিসকানেক্ট হয়ে গেছো? You have been disconnected. Please reconnect yourself. Um, hello everyone. So Dr. Majumdar have somehow unfortunately disconnected, but please wait a little while. He will be getting back soon. Everyone, can you hear me? So
Yes, we can hear you, sir.
okay, so please wait a little moment. He had just somehow disconnected unfortunately, and he'll be back soon. Thank you for your patience. Proceed. Okay, Wi-Fi তে করছো, ঠিক আছে। Let me make you presenter. Yeah, I'm making a presenter. Let me see. Can you switch on your mic, please? Can you switch on your mic? Yes. Can you talk?
Can you hear me? Yes, আমি কিন্তু কথা বলছি। Hello, can you hear me?
Yes, Santunda. That's all.
We
That's
can
all.
hear you.
Sorry, I don't know what's going on. Actually, there is a thunderstorm going. Can you hear me now?
Yes, sir, we can hear you.
Sorry, there's a thunderstorm going around. I don't know if it's because of that. I'm using broadband Wi-Fi. I don't know why that got disconnected. I'm sorry about it.
It's fine, sir. It's fine.
Okay, can you see my screen now?
Not yet, sir. Yeah, now it's visible.
Yes, sir.
Okay, I'll try and fast forward it a little bit because I think we've lost around 5 minutes already. Okay, so as I was saying that the another model is reduction model of iron oxide hydroxide. Iron oxide is a group of minerals that is like, for example, biotite, goethite. You have FeO3, Fe3O4, 2H2 is like things like that in your sediment. And what happens is when your aquifer is getting reduced, then these sediments, they usually bear a lot of arsenic on top of their surface, so they break down, and in that process they release arsenic to your water. So what will happen, you will have arsenic +5 and iron +3 system, and after the reduction you will have arsenic +3 and iron +2 system. So that's how it works, and it is the most accepted model, I would say, around the globe regarding the arsenic mobilization in groundwater. And there are other methods like competitive models where you have different, because once you have the arsenic release in water, they remain as oxyanions. They are not really elemental arsenic anymore. So these are like ASO4 2- or AS2A3 2- or ASO3 3- like that. So all these oxyanions, they start competing with other anions in your water, for example, phosphate, bicarbonate, silicate, etc., for different mineral absorption sites, because all these minerals have adsorption sites available for these ions, and they start competing with each other for these particular sites. So usually the more stronger ones, or the ones which have more absorption affinity, they kicks out the other one. So if you have a phosphate, it has a stronger affinity towards iron surfaces. So once you have a lot of phosphate, they can kick your arsenic out of the mineral surface and release them in water. So that's another one. And there's another one called the microbiological model, but it's basically a kind of a part of the reduction model where the reduction takes place with the help of metal-reducing bacteria. There are a lot of microorganisms in the waters, natural waters, so they actually help the reduction process. They catalyze the reduction process while they have their own respiration systems. So that's how it works. So these are the basic arsenic mobilization models that I would talk about. Okay. Now there are a few keywords that I have to mention before I move on to the main sections. One is, what are the redox ladder? The thing is, natural water, specifically groundwater, they're neutral, right? Why? Because these groundwater, they always interact with the sediments around it. So there is a lot of water-rock interaction going on. And what happens is, because of these water-rock interactions and mineralization processes, you have different ions, being a cation or anion, coming into your system. So you have a lot of different anions like nitrate, sulfate, phosphates, etc. And you have a lot of cations like ammonium, iron 2+, manganese 2+, etc. So your water, like after all these anions in your system, your water is actually balanced in terms of charge balance. That's why your water is basically neutral. You don't really have a lot of electricity coming out of your water, like natural groundwater. So, but the thing is that once you have these ions in your system can have different redox system, processes going on right now, as you can see here. And this particular staircase-like model is actually called the redox ladder. So depending on the amount of dissolved oxygen you have in your water system, you can have different, reducing redox status going on in the system. So if you have a lot of oxygen in your water, it is an oxic system. Mostly the surface waters, because they are completely exposed to atmosphere, they are generally the oxic system, and that's why you don't really get a lot of arsenic in surface waters. It's mostly in groundwater and different other waters. Then you have a suboxic environment where you can have a manganese 2+, manganese 0 systems. Then you can have a sulfate-rich system. What happens is that once you have a high oxygen system, low oxygen system, then your sulfate can get reduced to sulfide. And that's why, in marshes, for example, in marshland, you smell this hydrogen sulfuric, these smells, right? Because you have a lot of sulfide there. That's why you smell those marshy smells. It's not always about methane coming out. Because methane, as you can see here, needs even more reducing system. It's absolutely inhospitable for most of the oxic environment species. It's mostly very, very rare, extreme microorganism that exists or strives in this particular system. It's the extreme reducing environment that you can get. So so methanic system is another one. Now, so when I talk about redox, the reducing and oxidizing species that I've said, for example, sulfide and sulfate or phosphate, iron 2, iron 3, why is it coming out? Why am I saying the redox? How do I measure it? So I measure it with something called the redox potential that we all know, that we calculate from using the Nernst equation. So depending on how much of your cumulative reducing or reduced species you have in your water and how much of the oxidized species you have in your water, you can actually calculate using the Nernst equation the EH value, right? And once your EH value is negative, of course you have a lot more of the reduced species in your system. So when I say that arsenic 3 is more predominant in reducing environment, as if as in our case in West Bengal, that means you have a lot more reduced species. That is, you have a lot of sulfide in comparison to sulfate in water. You have a lot of phosphate in comparison. Lot of phosphate in water. You have a lot of iron 2 in comparison to iron 3 in water. It's a very easily visible evidence of it. I don't know how many of you have noticed it, but in our water systems, once you use these tube oils, right, to withdraw groundwater from your backyard, once you pump a specific amount of water and keep it in a clear vessel, in a clear bottle, what you would see is after a certain amount of time, you will see your iron deposition, right, coming out of it. You see these red iron deposit at the bottom of your bottle. Why? Because you have a lot of iron 2 in your actual groundwater system, because it's a reducing system. The moment you expose it, you withdraw it and then you keep it in a bottle and you expose it to the environment, because of oxidation, you get these iron 3 oxide precipitates. So that's how we know that our system is a very reducing system, and that's why we have a lot of arsenic 3 in our system. Anyways, another thing, is very important thing to know, is the hydrologic cycle. I'm sure most of you already know about it, that you have different, biosphere, atmosphere, hydrosphere in our system. And from your hydrosphere, your water gets evaporated, goes to your atmosphere in form of moisture. And then from there, it gets condensed and it comes down as precipitation in form of rain or snowfall or whatever back. So why is it important? Because to track a groundwater mobilization process, it's important to use something called environmental tracers, or it's basically like a DNA fingerprint, So in case of water, we use these stable isotopes as these fingerprints. We call them the water fingerprints in our case. So we usually use, in terms of stable isotope, we usually use the hydrogen and deuterium system or the oxygen 16, oxygen 18 system. The thing is that we use these, just to give you a glimpse into it, once you have this equation, you can actually calculate the ratio, which is the relative abundance of deuterium hydrogen in your sample, and then you can compare it with the standard, which is called as the SMW standard. This is Vienna standard oceanic water. And then you can express them in terms of per mil, not per cent, So it's per hundred, not per 100, it's per 1,000. Now, why is it important? Here's the chemistry part. So when you have, for example, these hydrogen isotopes, obviously the deuterium isotopes are much heavier, right? Like at least double heavier than the hydrogen isotopes or hydrogen with the counterparts. So when the water from ocean gets evaporated and it tries to go from the hydrosphere to reach the atmosphere, obviously your deuterium, because it's much heavier, will take more time to reach there. So you will not have as many deuterium as you would have hydrogen in your atmosphere. And that gives you the isotopic fractionation. And using that particular specific form of mechanism how your water is moving from one system to another system, as I just mentioned in case of evaporation in this case. And same goes for the data 16 and data 18 system. So what it means? It means that when you have a higher number of heavy isotopes, it is more, so your final data D value or data O value would be more positive if you use this equation. That means it is much older water. It's not the fresh water. When you have more of the hydrogen in your system, it would be more negative. So negative means it would be much fresher water. Why? Because older water would allow the time for the hydrogen or for the deuterium to move enough amount of deuterium to move into the next compartment. But if you have fresh water, that particular water system didn't really have that time to allow for the deuterium to move from one system to another. So in a nutshell, when you have a negative value of delta D or delta O, 18, that means you have a more fresh water, more young water. Sorry?
No, sir, you continue.
Okay, I heard somebody.
Those are nothing to do. Please come.
Oh, okay. So that's very important to remember because that's what is going to be applied in my next. Yes, okay. So let's start with something called the monsoon. Why? Okay, so as I said, that the groundwater system in our study, it's well known. Everything has been reported. How the arsenic is coming into the system, what are the mechanisms and everything. But what was never done before we did it is how the natural recharge process is actually influencing the groundwater chemistry in your system. And the major recharge process in our area or across India is of course monsoon, right? So you have this huge rainfall coming out of nowhere, of course, from the sky, and then it can change everything, the entire hydrologic cycle or the course of it, right? Suddenly, in a very quick time. So that's what we wanted to study. Now, so the objective was to investigate for the first time how monsoonal recharge is going to, process the arsenic release and its speciation. Because remember, speciation is the most important thing. Because as I said, one particular species is more toxic than the other. So there is no point of measuring the bulk arsenic only. It's important to know whether it's inorganic or organic, and if it is inorganic, it's important to know if it is 3 or 5. So it's important how monsoon can influence your speciation as well. Another was to relate a bit of geomorphology, geochem to the geochemistry. I'm not going to get into a huge detail of it in this case. So as I already mentioned, we have used stable isotopes to track back the groundwater flow systems. And we also used another environmental tracer called chloride-bromide molar ratio. Why? Because in groundwater, chloride and bromide, they both act as a very conservative ion. We have talked about different ions. But unlike sulfate, phosphate, those kind of redox ions, chloride and bromide in general are very, very conservative thing. So when you have chloride-bromide molar ratio together, any change in your system can actually change the chloride-bromide molar ratio, and you can actually say that exactly what has happened, what were the mechanism, or what are the modes or rates of groundwater recharge that change that particular chloride-bromide molar ratio. Because individual chloride and bromide should not get affected by these processes. So once you have the chloride-bromide molar ratio, that can get changed. Okay. So these two we have applied to understand the things. Now, as you can see, these red dots are samples from a floodplain area. What is a floodplain? It's a lowland area where you have a high contamination of arsenic, and then you have also collected samples from natural area. What is natural area? It's a high area with a high flat relief, So it's usually near the road, near the station. You build the roads and station around the natural area, because you don't want your roads or railway tracks to get flooded. So that's why natural areas are built and all that. Anyways, so when you collected sample, the most interesting part is what we have observed is based on these ions, as I've already mentioned, the floodplain area were even more reducing than the natural area. And what has happened is, after monsoon, these reducing environment gets increased. What does that mean? That after monsoon, the reducing ions, they gets increased in your system for some reason. And not only that, the most important part, your arsenic concentrations gets increased by more than 200% in both these areas. Specifically the arsenic 3, that is the more reducing form of it. But in natural area, the concentration is much less than the floodplain, so that doesn't really matter, So in floodplain, you have an increase of more than 200%, which is not at all good. So you have to understand why that is happening. Now, if you see here, don't really look into these things, but if you concentrate right here along these samples and look at the, just follow the index here, the legends, these triangles are basically samples from the natural area, and these, you can say these rectangles are from the floodplain areas. Now, the yellow samples are the post-monsoon samples, and the white samples for both the cases are the pre-monsoon samples. What I have seen here, you see the floodplain yellow sample, that is the post-monsoon samples, there is not really much increase in in delta weighting values with the chloride concentrations. But with natural area samples, specifically in pre-monsoon, the chloride concentrations are not really increasing along with the delta weighting values. In another figure, in this one, when I compare the same delta weighting values with the arsenic concentrations, with the arsenic concentrations, you can see that again the floodplain post-monsoon sample arsenic concentration increases, but with that increase, you don't really have a higher or the increasing delta weighting values. Now, what it says, as I said already, when you have more negative delta weighting values, that means if you get down through this axis, it is younger water. And when you have, if it is more positive, then it's older water. Now, if you compare these two figures, you have more arsenic concentrations when your water is much younger. That is, you are getting much fresh water. And along with that, you have higher chloride values of water. So high chloride value means you get high chloride values when usually you have a source of pollution, an immediate pollution that is recharging your groundwater. It could be sewage, it could be cow breakdowns or whatever. It could be open sanitations, it could be agricultural refuse, whatever it is. So if the chloride concentration increases immediately when you have this kind of very fresh water coming in. So that means, including these two values, we can say you get higher arsenic concentrations with floodplain post-monsoon specific samples when you have younger waters coming in, in your system. On the other hand, when you have older waters, you don't really have higher arsenic concentrations, as we have already seen in the case of natural, specifically pre-monsoon samples. Now, another thing is, we can skip this part, okay, just a bit of it. So here, these rectangles are the pond water samples, and we have measured the delta H and delta weighting values of both of them as well. So when you have measured that, you can see that pond water and rainwater, these stars are rainwater samples that we have measured. So both the pond water and rainwater samples are actually falling closer to the floodplain post-monsoon samples, which means that there is or there possibly a link between the rainwater or pond water samples that is recharging your water with young water, fresh water. That means immediately after the monsoon, your water systems in floodplain areas are getting recharged, and that's why you are getting high concentration of arsenic. But why? Because arsenic is not directly related to isotopic values, right? So this is why. When you have waters, or see the concentration of dissolved organic carbon. DOC is dissolved organic carbon. That is the measure of organics in your system. How much of humics or fulvic acids you have in your sediment or in your water, dissolved in your water. So when you have measured them and along with the bicarbonate system, you see along with the floodplain USTM post-monsoon samples, there's a linear relation with DOC as well as bicarbonate. That means that when your water, as we have already seen that your post-monsoon floodplain samples are getting a lot of fresh recharge from monsoonal water or from pond water. Now, what do the pond have? These ponds actually host a lot of these organics, lot of these organic carbons, and these organic carbons are getting into your system. And what happens, as I've already mentioned, if you remember, that the reduction model it actually gets aided by microbial systems. Once you have microbial system, that can catalyze this reduction of iron oxide hydroxide that would finally release arsenic in your system. So these microbes they use these dissolved organics as their respiratory method. And once that happens, they actually, transfer electrons to your arsenic or iron host systems. So once you have these iron 3 systems hosting arsenic 5 in sediments, these microbes releases one electron. Those minerals acts as an electron acceptor, gets reduced, and finally releases the arsenic in your water systems. So that's the reason, possibly, why you're getting a lot more arsenic in floodplain, specifically after the monsoon. Now, you don't really have to look at this thing, but in specifically this one, you see the floodplain samples right here are the only ones, or mostly, they are reaching this methanogenesis state, as I said, in the redox ladder. That means they are getting to a state of enough reducing environment where these iron minerals are getting reduced aided by the microbiological system using the available organics and releasing arsenic into water systems. But why is it that only arsenic 3 is increasing way more than arsenic 5, as we have already seen in the first picture? Maybe because there are researchers that say that there are bacteria or microorganisms in your system that could directly, if they reach a certain state of reducing environment, they can directly reduce your available arsenic 5 to arsenic 3. So that means you don't really need additional amount of arsenic 5 coming out of your sedimentary environment. Whatever arsenic you have, arsenic 5 or 3 in your water, once that state of methanogenesis or whatever, that the state of redox environment has reached, these microbacteria can actually reduce your arsenic 5 to arsenic 3 on their own. So that's why maybe you're getting more of arsenic 3 than arsenic 5, which is really an alarming thing, because we get a lot of monsoon in our study areas, and once you have a lot of arsenic 3 after the monsoon, then you have a bigger or larger task in your hand to control it or to remediate it, right? So, in concluding, as I already said, that it's very important that the monsoonal recharge is actually affecting your groundwater chemistry and releasing a lot more arsenic 3 in your system than arsenic 5, specifically after the monsoon in the floodplain areas. Why floodplain? Because these floodplain areas, as I've already said, they are lowland areas with lot more ponds all around it. And these ponds are possible, we all know they host a lot of these organic carbons. So that's the reason why these floodplain areas are much more susceptible or vulnerable for these kind of geochemical changes to happen. Okay? Okay. Next, just a glimpse of the, because there are studies that say that, somebody is saying something? No. Okay. So the role, of course. So as I've already just shown that arsenic can get released or being hosted by minerals, right, in sedimentary environments. And these minerals can be of various kinds of sizes and shapes. This could be a large particulate sample, they could be colloidal sample, or they could be so small that they could only remain in the dissolved fraction of your groundwater. So that's what we wanted to see, that what fraction of these particles actually scavenging your arsenic and which form of arsenic again, because as I said again, the speciation is important, okay? So to do that, again, we have collected samples from these study areas, and after collecting samples, so what we did, we have run through these samples using different filtration levels. So we have used 0.45 microns, 0.22 microns, 0.1 microns, and 0.05 microns of different cellulose nitrate membranes to filter these samples. And we have collected these different fractions of sample to see what are the different fractions happening in a sample. If you see here, immediately after 0.45, for all these samples, most of the arsenic actually remains in the dissolved fraction. Why? Because you see, even after the 0.05 micron of filtration, that is the smallest of all these filters used, almost 80 to 90% arsenic remained in the dissolved phase, and we consider that after the 0.05 filtration, whatever particles are there, they are actually in the dissolved phase. They are suspension, they are dissolved suspensions. So you see that arsenic, mostly 80 to 95% of this arsenic concentrations, they remain in the dissolved phases. But there could be samples, for example, as if like sample number 5 here, you see after the immediately after the 0.45 filtration, there is a decrease of around 60 to 70% of arsenic. That means that most arsenic were actually scavenged by the particulate phases. So that's why we have immediately after the 0.45 fraction, we have these particulate phases that are scavenged arsenic, and you are only left with the 30 to 40% arsenic. Now, why do we need to do so? It's very important to understand. All around the world, whenever arsenic research happens, they always use these 0.45 microns filters to sample arsenic. Why? And sample arsenic to analyze whatever they want to do, analyze it or propose remediation measures. They use 0.45 microns. Why? Because they want to get rid of these particulate phases. Because these particulate phases can clog your instruments, and these instruments are very expensive and sophisticated ones. I understand that, but the problem is that all these remediation strategies or the removal techniques that are there installed in these rural areas, people there, they don't understand what is particulate, what is the colloidal phase or the dissolved phase. They drink water directly from the wells, right? So they don't use 0.45 microns. So it's important to understand before suggesting a strategy or remediation policy, it's important to understand how much of your particulate phase arsenic is actually getting scavenged away, or what are the changes of the arsenic species in that particular fraction as well. So that is why we wanted to do it as well. Now, if you see for different samples, here these bars, the black ones is actually for the percent of iron remaining after different filtration steps. The gray one is for the dissolved organics, and the white one is for percent of aluminum. Why? Because all these the minerals that we have documented, they are mostly of iron or aluminum phases, and the organic carbon phases. That's why I have used these three to see how the arsenic concentration is correlated in these different fractions, along with the change in these three particular different mineral phases. As you can see, for different samples, we have different results. For some of the sample, you have this the change in arsenic. For example, here when at the very beginning, that is during the larger colloidal fractions, and then in the smaller fraction of it, they remain pretty much constant. For others, if you see, the change is just the opposite. You have a very steady state of arsenic concentrations during your larger fractions, and suddenly they start to get scavenged away in the smaller fractions. And along with that, the percentiles were very variable. That means that in some cases you have these larger iron or aluminium colloids, which are inorganic colloids, scavenging arsenic, and in some cases you have smaller organic colloids or organometallic colloids, I would say, that is scavenging your groundwater arsenic. So it's very variable. And what happens when you see arsenic 3 and arsenic 5? So this is arsenic 3 and this is arsenic 5. As you can see, throughout these fractions and stages, even arsenic 3 and 5 behave differently. There are samples where they differ like in a similar manner. For example, sample number 3, 4, or pretty much sample number 6, they behave similarly. But the rest of it, you can see they differ differently, they behave differently. That means it's very important to measure arsenic speciation as well throughout these fractional stages, because it's not universal. It can change from one sample to another, and if we don't know what's actually changing it, we can't really propose a proposal model, a remediation strategy. So what happens here is, if you see, in most cases, the arsenic 5, I'm talking about the overall picture, So in the arsenic 5 is actually getting decreased during the smaller fractional stages. But arsenic 3 is getting scavenged away while you're filtering using the higher fractional filters. That means maybe that arsenic 3 is getting scavenged by a larger, as I already said, the larger inorganic iron aluminum colloids, and arsenic 5 by the smaller organometallic colloids. So is it true? We wanted to see if it is true. So after all the filtration stages, that is after 0.5 micron, 0.05 micron, and starting from 0.22, we have try to see what is the correlation of arsenic along with the three different phases. And as you can see, at the very beginning, when it's like 0.45 micron, arsenic correlates mostly with iron and very less with GOC. That means the larger fractions are dominated by the iron or aluminum in some cases, inorganic colloids. But if the more you come down the smaller fractions, right down to here, where it is the 0.05 micron, you can see the arsenic is actually correlating a lot with the DOC concentrations. That means, as we have already mentioned, that maybe in the smaller fractions, the arsenic is actually scavenged by the organic colloids, or it could be the organic metallic colloids as well. Now again, is it true? So what we did is we tried to collect these colloidal samples right after the 0.05 fractionation stages, and we wanted to see what are the morphological features of it. What I've got from these colloids is, we have got, of course, the iron, arsenic, and in some cases aluminum as well. But along with that, we have got large peaks of carbon intensities. That means, as we have already thinking of, that these small fractions of colloids are actually could be consisting of both inorganic and organic colloidal fractions. We wanted to re-emphasize on the fact, and we went on to carry out a FTI study. And as you can see, there's a large hydroxyl hump here because of this is water samples, right? So you've got to get this huge hump here. But if you see these asymmetric carboxylic intensities right here, specifically the 1624.1 and 1636 peaks right here is actually related to organometallic or organic natural organic matter and iron and arsenic colloidal sample. This actually corresponds to compounds consisting of arsenic, iron, and natural organic matter. So this kind of proves our hypothesis or the idea that this could for the lower fractions, there could be the organometallic fractions that is scavenging the arsenic in groundwater. Why is it important? Because most of the remediation strategies or the removal techniques that is available across the world or in our study area are ultrafiltration strategies. The problem is, as we have already seen, that most of the arsenic remains in the dissolved fraction, right? So even if you have an ultrafiltration technique going on to remove arsenic, you will not be able to do so because your arsenic remains in the dissolved fraction. You need nanofiltration, and nanofiltration is very, very costly. So what is better to do is you can actually oxidize these arsenic concentrations using alum coagulation or whatever the other thing, and then you can precipitate your arsenic 5 along with your arsenic 3 mineral phases. That is more suitable than the ultrafiltration strategies, because that may not work in most of the cases. So yeah, that's the concluding remarks pretty much that I've already said. Now let's move on to the analytical aspects. Talking about removal techniques, as I was already mentioning just before this slide, there are various removal techniques that have been suggested across the world by various groups researchers, and they are actually patented, they are being used in large scale, in community case. Some of them are very good, very, very efficient to remove arsenic. But the problem is their operational and maintenance cost is really, really high, very, very expensive. And there are some other methods available which are not that expensive and easy to use, but they're not that efficient to remove arsenic, you know. So we have to balance somewhere in between these two. Okay, so the best option, of course, in these cases is to supply treated surface water. You know, you can treat your river water and then supply community water supply system. You can have a network of community water supply system, and then you can resolve the issue. But the problem is what we have seen in rural areas, it takes a lot of time and also money, because there's a government involved, there's a policy makers involved, so it takes a lot of money. So what you need for the time being, a technique which is very easy to use, very cheap, as well as pretty precise or pretty efficient to remove arsenic as well. So we have been thinking to do that, and in one of the researchers from our group, has actually devised a removal method for groundwater arsenic, which is called the SORAS. What SORAS? SORAS is solar oxidation and removal of arsenic. So SORAS is a completely green method, uses all the natural ingredients in the environment to remove arsenic in your water. What do you need? You need sunlight, and you don't have to pay anything for that, right? You need a lot of iron 2 in your system. Thankfully, again, we have loads and loads of iron 2 in your system. And you need a chelating ligand or a complex shedding agent to keep this iron 2 or iron 3 redox couple in your water for the longer period time in circumneutral pH ranges. And for that, we tried, because we've seen that there was an idea that was derived from the Fenton type reactions, photochemical reactions, but we've seen that you have a carboxyl system that can give rise to a lot of superoxide kind of free radicals. And these free radicals are very, very strong oxidants, right? So what we've done, we've added simple lemon juice, a few drops of lemon juice, which have a lot of citrate in it. What happens is that your citrate is actually, it forms a complex with the available iron 3, because what happens, you have the solar light coming in, and your solar light, specifically the UVA range, oxidizes your iron 2 to iron 3, and anyways you are exposing your water to atmospheric oxygen. So once you have the iron 3 forms a complex with the carboxylic acid groups with the available or the added citrate juice. Once that happens, because of this photochemical reaction, they produce a lot of these superoxides that are really, really strong oxidants. And these oxidants oxidizes your arsenic 3 to arsenic 5, and the arsenic 5 gets co-precipitated along with these iron 3 oxide oxides, because you have iron 2 already oxidized to iron 3, so iron 3 will have iron 3 oxide iron 3 oxide oxides. So on top of their surface, they will absorb the oxidized arsenic 5, and they get co-precipitated. So they will get out of your groundwater solution or drinking water as precipitates at the bottom of your bottle. So that's exactly what we have formulated called SORAS. It's being used in various countries around the globe, starting from Vietnam, Cambodia, which are very, very highly contaminated groundwater systems. Now, after that, what I have already tried to do, or try to extend this work a bit more, is to see which are the more stronger or efficient complexating agent, or which are the natural ingredients that could be more efficient in addition to lemon, adding citrate to this system. So, so this was the reaction method that I was talking about. When once you have the iron 3, they form this three citrate complex that produces these superoxides, and then the reaction goes on. It's a cyclic reaction, and it goes on and on and on. So, And you can actually, because of this cyclic action, you can actually have an efficiency of around 95% to 98% of your arsenic removed from your system. But remember, this is a household method. It's not a community method. So any household for a family of 4 or 5 can do that. Say if they drink like 2 to 3 liters of water every day, each individual, they can have 10 to 15 bottles of water, and they can run this process at the household level. And that could satisfy the drinking water need for a day for them. Anyways, so what I've done is I've tried other things apart from the citrate source from lemon. What are they? I tried, apart from lemon, lime and tomato. I don't know why that came to my mind, because I thought that in lemon and tomato and lime, they all also have, they do contain a lot of antioxidants as well. And I was going through research that say that antioxidants can produce superoxides as well. So that was the thing that was going through my mind, and I already had this method established. So I tried to see what would happen if I use tomato, lime, and lemon instead of only lemon. And as you can see, you have these PET bottles, this polyethylene tartalate bottles. You can fill this bottle with keeping a little space out here, because you want the atmospheric oxygen to get in and unsaturated water system. And you can see after 2 hours, you see the precipitates are starting to coming out, and this is at the end of the 4-hour exposure time. So it's only 4 hours of exposure, and you can have your system, without the groundwater arsenic in your drinking water. So what I did is I made a matrix like this with these 3 different ingredients. And what are these? I tried to see what are the effect of different arsenic and iron molar ratio. Because remember, iron and citrate are the most important natural ingredients you need for this method to work. So I varied these concentrations along with arsenic concentrations as well. And I tried the same with for both synthetic samples and some of the natural spiked groundwater samples as well. So what I found out, and if you see, the arsenic concentration starts from 0.5, 0.25, 0.1, so high concentration, low, medium concentration, low concentration. Same with iron and citrate. Iron is 6 ppm, 4 ppm, 2 ppm, and the citrate dose was 0.5 ml per liter, 0.75 and 1. So I varied them. So I wanted to see what are the effect of the arsenic iron molar ratio on the particular reaction that is going on in the system. So what you're seeing here is for both arsenic iron molar ratio and citrate dose, there is a centralized optimum tendency. That is, when your arsenic and iron molar ratio is in the middle, it's not too high, not too low, your system seems to work more efficiently. Same with citrate dose. When you have a citrate dose of moderate citrate dose, not too high, not too low, same thing happens. So that is something we need to keep in mind that we realized. And we were also trying to think that why it is that, if you see here, that tomato is the most efficient one in comparison to lemon and lime being the least efficient one. Why is it so? We are trying to think, because we have seen when we were going to literatures that antioxidant activity of tomato, lime, and lime, tomato has the least antioxidant activity. That is, it is least conducive towards the photochemical reactions, even if they all have the antioxidants. So what we found out is it's not only the quantity of antioxidants in these natural ingredients, it's also the quality of it, the nature of it. So if you remember the right expression here, remember I wanted to keep it here because you always keep in mind that you need these carboxylic groups to have these reactions to work, or the cyclic process to, because you need to have this iron 3 organic complex in order to have these superoxides to work. Now, in lemon and lime, you mostly have antioxidants like flavanols, like taxifolene, alendronine, or nalurine. On the other hand, whereas you have more like hydroxycinnamic acids in case of, hydroxycinnamates in case of tomato. So you have p-cumaric acid either or ferulic acid with these available carboxylic groups, in addition to the already available citrate groups in all 3 of them. So this is why in tomato you have these additional carboxylic groups aiding your photochemical reaction by producing more of the superoxides in order to have or give more, efficiency when it comes to get rid of your arsenic in groundwater. So that's what we have established, and as you can see, it's a very easy method for the time. Again, it's not an established method for community supply, but until and unless these rural villages have it, they can easily use this technique, and many of them are already using it in household levels. Okay, so that's what it is. Okay, so yeah, I've already concluded, I guess. So I'm trying to not to run out of time. So let's go to the most important part of it, which is the development of eco-friendly strategies. Now, before going there, so what are the objectives? The objective was to, so I have been talking about arsenic, right, all throughout this talk. But it's important that you have to measure arsenic, right, in groundwater flow or sediment or whatever. And to measure that, you have to need, you're going to need a analytical technique available in your laboratory, right? So, and there are many techniques available, but the problem with most of these techniques are, again, either they are very, sensitive but very expensive, or they're not that sensitive, but not that expensive but not sensitive as well. So we wanted, and also in addition to that, most of these techniques uses a lot of organic solvents for this analytical process to work, and that's not eco-friendly at all. To use volumes of methanol or acetonitrile for chromatographic systems, right? So what we wanted to do to establish or to develop an analytical system which could be not expensive, not but sensitive, very sensitive as well, and it should be a green technique as well. It should somehow avoid using these volumes of organic solvents throughout the process. So that was the major objective. Now, coming to, as I was saying, that there are many arsenic determination methods available, not only chromatographic or hyphenated techniques like HPLC ICP-MS or HPLC ICP-AES, which are the most used techniques, but very, very expensive. But then you have electrochemical techniques as well, which are not that expensive and pretty sensitive, but they have problems like matrix interferences as well. Like you can have the cathodic stratic voltammetry or anodic stratic voltammetry, things like that. And the most old one to measure arsenic was the colorimetric method using the JEC method, where you usually generate arsine gas, a reduced form of arsenic, and then you impregnate that thing in a paper merged in mercuric bromide to form a color, and you can then measure the color from that particular paper. So these are the measure techniques that you can use. But as I said, there are problems that we wanted to solve. Now, to solve that, so in addition to chromatographic technique, as I said, the hyphenated chromatographic techniques are the most common ones that measure arsenic in groundwater, like HPLC, ICP-MS. But the problem in HPLC, again, that we need to use a lot of organic solvents. Then there's a problem in the hyphenated interface between the HPLC and the mass, the ICP-MS mass spec detector that you want to use. So what we can do is actually run a pre-concentration technique. What is that? It is actually enhances your sensitivity. How? You pre-concentrate your sample. That means whatever concentrations you have in your particular analyte, you can actually enhance your concentrations. How? Now, you can have your analyte, in this case arsenic, in water, and then you can extract that arsenic or the any other analyte from the higher or larger volume of water to a much smaller volume of organic solvent, which is hydrophobic. So what happens is, because you're extracting your analyte from a larger volume to a much smaller volume, you are pre-concentrating it. Your concentration is getting increased. It's a very easy technique to use. Initially there was liquid extraction methods, but what has been used now is there are different kinds. One is liquid extraction, so another one is solid phase extraction. In solid phase, what you do is use a solid solvent as a microbead, and then you solve the analyte from your donor phase in which the analyte was in. That is the groundwater in this case. Then you can have liquid phase microextraction, the one that we are going to talk about in detail in this particular thing. And then you can have solid phase microextraction as well. In liquid phase, what happens in liquid phase microextraction, you use the microliters of organic solvents, and then you, as I said, you extract your analyte from larger volumes of your donor phase, which is your water system, the groundwater. And in solid phase microextraction, instead of having micro volumes of organic, you can have a very small bed of solid polymers, coated on top of a different inert material, hydrophobic materials. So that's solid phase microextraction. But in our case, we are going to focus on the liquid phase microextraction. Now, liquid phase microextraction can be of different types as well. It could be single drop microextraction, dispersive liquid microextraction, hollow fiber liquid phase microextraction. I'm not going to get into detail of the other two, and I'll get right down to what we are going to talk about is the hollow fiber liquid phase microextraction. What happens in hollow fiber? You use this polypropylene hollow fibers. These fibers are very tube-like microporous tubes. And in these tubes, what you do is you use organic solvents, you purge or inject organic solvent inside the pores or in the lumens of these hollow fibers. And then you equilibrate these hollow fiber organic solvent along with it. You immerse the tube inside your donor phase, which is your groundwater in this case. And what happens after the equilibration, that you extract a lot of these analyte, in our case arsenic, to within your organic solvent. You pre-concentrate. The problem here is that metal ions, just like arsenic, are not hydrophobic. They are hydrophilic. So the problem is it's not easy to extract them from water system, matrix, or water, or from water to an organic solvent. So what you need to do, we need to be a complexing agent called extractants. In order to have an ion pair, just like chromatography, in ion pair-like situation where these ion pairs or the created ion complex is hydrophobic. So you're turning your analyte from being hydrophilic to hydrophobic, and in that way you can extract that particular analyte. Now, hollow fiber liquid phase microextraction can be of two different types. As I said, you can inject your organic solvent inside these the pores as well as the lumen of your hollow fibers. So, if you have your organic solvent in both your lumens and the pores, then you are extracting the analyte from the water to your organic phase. That is two different phases, water to organic solvent, right? But there could be another process where you can, after injecting the organic solvent, you can inject another water, you can say accepting phase, which is water, in order to extract or re-extract your analyte from the organic solvent to your water, to aqueous phase again. So what happens is, in this case, you have the donor phase outside the fiber, you have the organic phase inside the pores of your fiber, and then you have the aqueous phase, the second one, that is the acceptor aqueous phase, inside the lumen of your fiber. So this is basically a three-phase system. Now, let's see a diagram. So this is a 2-4 system. As you can see, these are the fibers inside, dipped inside these vials having your donor phase or the aqueous sample. And inside these fibers, so if it is the donor phase, that is your aqueous sample, and if it is the membrane phase, in the membrane phase, being it the pores, that is, and then you have the acceptor phase inside the lumen. So in two-phase system, you have the organic solvent and the extractant inside the so both the pores of your fiber and the acceptor and the lumen. So what happens is, when after the equilibration, the analytes, that is these the blue balls, the analyte from the aqueous phase goes through the pores and then gets extracted inside the acceptor phase. So you have an organic acceptor phase after the end of the equilibration inside the organic solvent. In three-phase system, everything remains same. Only thing is, as I said, you inject an aqueous phase after injecting your organic solvent, in excess, so that you have an acceptor. and you have the organic solvent and extraction inside the pores. So what happens here? Your analyte goes through the pore, having the organic solvent and extraction, and getting accepted or trapped inside the atmosphere of the inside the lumen of the hollow fiber membranes. So that is the basic difference between the two. So we have tried both. After equilibrated and having extracted or having run the pre-concentration technique and pre-concentrated the analyte, we take the analyte and then we try to analyze with something called the TXRF instrument. It is a total X-ray fluorescence instrument. Why? Because we are not going to use mass specs. They are very expensive, very operational costs are very high. The cooling media needed for the detectors really needs a lot of electricity, so again a lot of cost there as well. So we have used something called the total X-ray fluorescence. We didn't develop it, but we kind of added this particular technique. It's a very, very handy to use a benchtop, small benchtop technique. But remember, this one is a multi-elemental technique as well, just like ICP-MS or AES. AES is not a multi-elemental technique though, but anyways, so it can almost measure about 70 to 75 of the elements in the periodic table, just with one small single instrument. So once we have the pre-concentrated analytes coming out of our system, we use the TXRF instrument. So, and what we do, we drop microliters of this analyzer on top of this reflector, and top of a reflector, and then from the reflector, this is the sample support of reflector. You send this X-ray source, X-ray beam, and what happens is here is a total reflectance happens. Why? So the total reflectance causes your background intensity to get reduced. And not only that, it also incites excitation, further excitation. So what would happen is the X-ray beam it will excite your available light for further fluorescent excitations. So you will have a doubling of intensity. So you will have a higher sensitivity for the instrument or for the detector to detect your signals coming out. So that is why it's a very, very sensitive instrument as well. Okay, now what we do, so you will get this kind of spectral ranges, and you can use the K alpha or K beta lines to measure your analytes. Okay, now objective I've already mentioned. So this is pretty much the schematic setup of your experiment. This one is the 2-phase, this one is the 3-phase. So you run the experiment, you get the analyte, you deposit your sample on top of a quartz reflector, you preheat them or heat them to make, to dry out the droplet on top of the reflector, and then you analyze it with the TXRF measurement. Okay, now before getting into the actual pre-considered measurement, it's very important to have the right solvent, the right organic solvent and extractant combination, because there are many, and each of the analytes behave or react differently to these combinations. So when we tried 4 different extractants and 3 different solvent combination for arsenic 3 and 5, here in this case aliquot 336, Cyanex, TLA and TBP, tributyl phosphate, along with for the solvents 1-octanol, dodecanine, 4% dodecanol, and cumene. As you can see, only 1-octanol and aliquot 336 was the combination that worked for arsenic 3 and arsenic 5, because for the rest of them, we had a problem of third phase formation or suspension, micellar formation. You can see here, right here, you see these white precipitate-like suspensions coming out of this system, which are not good for our analysis. So we, discarded all the different combinations, and we focused on the aliquot 336 and cumene dodecanol system. Now, you can see for the aliquot, since as I said, it's ion exchange kind of extractant that complexes your anions, the ion exchange process, and make it more hydrophobic in nature. And in terms of fiber, we use two different types of fibers. One is with a smaller internal diameter, another one is a larger diameter. Now, for the 2-phase system, we tried both the smaller diameter system and the larger diameter system. And as you can see, in terms of the intensity of the analyte using the TXRF instrument, it was random. The RSD values was around only 37% to 17%. So we had to discard the 2-phase analytic system. This Could be due to the, because in two-phase, if you remember, your analyte solvent is organic solvent, and while analyzing with TXRF, you have to deposit your organic solvent on top of the these quartz reflectors, and it's very difficult to dry these solvents. Why? Because one of the major criteria of selecting these solvents is they have to be very low volatile solvents for pre-concentration to work. And because they are low volatile solvent, it's very hard for the TXRF reflector to dry out the analyte completely. So maybe this is one of the reasons. Now, when it comes to three-phase, we have while working with the two-phase system, we faced a lot of difficulties with the smaller diameter membranes, mechanical problems. While rotating it or agitating it, it fell off or things like that happen. So we stick to the larger diameter, more strong, mechanically stable, larger diameter S6 fibers. And what we did, if you see here, so the feeding phase is a donor phase. That is your your sample system. And then you have a stripping system. Stripping system is the accepting this atmosphere inside the lumen, if you remember. And the membrane phase is the one that is organic solvent with the extraction inside your porous system. So when we ran our deconcentration technique or experiment with three-phase system, we have got really, really good results. But before that, it's very important to systematically standardize different parameters that could affect your analytical results, both for the pre-concentration method and for the TXRF. So what are they? So they are the equilibration time, that is the kinetics. They are also the amount of extractants to be used, the concentration of extractants. The pH is very, very important, and the agitation speed while having your equilibration experiment going on. So if you can see, with higher concentration, like we have tried many other concentrations, but if you see, we have kind of focused on mine in these three, and with higher concentration of extractant concentration, that is 0.2 molar, we got more of efficiency or extraction efficiency, both for arsenic 3 and 5. But in case of arsenic 5, the system works better than arsenic 3. For extraction time, as you have already seen, as you can see, at 4 hours, the equilibrium is reached, and then it gets. So the kinetics tell us that it's 4 hours is the time that you need to run your equilibration experiment or the three-phase pre-concentration experiment. Again, the arsenic 5 worked better than arsenic 3. But pH is the most important thing here. As you can see, and let me remind you that we standardize this parameter one at a time. Okay, so we kind of fixed everything else and changed only one parameter at a time. Okay, to have to observe the best results. Now, coming back to pH, if you see, arsenic 5 is getting extracted maximum at pH 8.5 or kind of circumneutral pH. But arsenic 3 is getting extracted at around pH 13. Now, this is the very fact that gave us the liberty to speciate arsenic 3 and 5 using the hollow fiber liquid filled micro extraction system. We don't need the chromatograph or HPLC to speciate it, So because at different pH, you just use different pH systems, and you can speciate the same sample in terms of arsenic 3 and arsenic 5, or separate arsenic 3 and arsenic 5 if you want to say so. For agitation speed, as you can see that you can have a higher agitation speed because they both show the same extraction efficiency. But in order to make things simple and don't have problems because of mechanical disturbance, we kept it to 440 RPM. Now, as I was mentioning regarding pH, remember I told you that arsenic remains as arsenic oxygen ions, and you see these are the arsenic 3 and arsenic 4 oxygen. This is arsenic 3 and this is arsenic 4 oxygen ions that are the predominant ones in in natural groundwater system. Now, if you see for arsenic 3, the maximum intensity you get of the most predominant oxygen ion, which is H2SO3, is around that particular pH, around 12 to 30. That is the reason why you are getting arsenic 3 more in that particular pH. But the problem why you are not getting as much extraction as arsenic 5 is, apart from, in case of arsenic 3, apart from this particular arsenic species, you have a different other ones as well, which can influence your extraction of this particular one, the most predominant one. But for arsenic 4, if you see, at the most predominant one is the AeSO4 2 minus, and the predominant one gets maximum remains maximum in concentration at pH 8.5. And it doesn't have the same kind of interference from other arsenic 5 different arsenic 5 species. So that is why, because it is pretty much exclusive, that is why maybe we are getting the arsenic 5 extraction efficiency much better than arsenic 3. Okay. Okay, now we also tried to see the linearity of our measured experiment, and as you can see, for both arsenic 3 and 5, our results are pretty linear, within the range of our experiments, from 0 ppb to our 250 ppb, which is the usual range, average range of arsenic you can get in your drinking water. But again, your arsenic 5 gives you much more gives you more linearity than the arsenic 3, but still for both arsenic 5 and 3 it can work because it's almost 0.99 in both the cases. But with arsenic 5, the limit of detection, when we calculate the limit of detection, it's 0.03 microgram per liter. Remember, the WHO guideline is 10 microgram per liter. So it's almost 100 times less. It's almost at nanogram levels. So not only water, you can use this system for many other, matrices where you have the arsenic problem, like blood, serum, or any other system like saliva, urine, food stuff. You can use the system because in those systems, the arsenic concentrations are much lower. So that's why you can go down as below as 0.03 microgram per liter using this one. In case of arsenic 3, it was 5 microgram per liter, which is still way below the guideline value. Okay, now using the TXRF, we had to standardize the parameters for TXRF as well. Now for TXRF, one thing is a very important thing is the deposition. As I said, if you remember, the two-phase system didn't work because of the deposition problem of the organic solvent. Here, so it's very important to have a standardized deposition system. So when we tried different deposition volumes, as you can see, depositing like 10 microliters of our samples at a time was the best one to get the best intensity results using TXRF. So that's what we did. And when you see all the while I've been talking about pre-concentration and all, this is the last thing. We're already like almost coming to the end. So if you see, we had two different systems, right? One system having 100 ppb concentration of arsenic, but without pre-concentrations. Another system with only 5 microgram per liter, that is 5 ppb arsenic, but with the concentration using the HFL ppb. And you can see the difference between the two in terms of sensitivity. The lower, like much lesser concentration in arsenic system gave us way more like sensitivity in terms of sensitivity in whereas you have lesser sensitivity without the pre-concentration. So this works really, really well in terms of increasing your sensitivity as well. We try to understand the reliability of the system, the reproducibility, and we try ran the intraday experiments as well for see for both the arsenic and arsenic 5. Again, for arsenic 5 it is better, but we got more or less like pretty good reproducibility of our results in terms of both intraday and inter-day experiments, with the RSD values within pretty much 0.5 to 1.5. We tried the same for different spiked groundwater because we wanted to apply our analytical technique for real samples, right? So we have collected different samples, we spiked it with different arsenic 3 and 5 concentrations, and we tried to see if our system is working. And if you see, again, our system is working pretty much well because this is the control, and then you have a mineral water system and a river water system and various groundwater systems, and you have, we have pretty good results, more than 80 ppbs of arsenic. So 80 to 95% of arsenic was actually detected from a solution of 100 ppb arsenic concentrations of a stock solution. So, of course, there are varying results for some of the groundwater results because they may have different interfering anions like bicarbonate, chloride, sulfate, etc. that could, cause the final result of your analysis. But overall, we can say that yes, our system is pretty much working, but more so for arsenic 5 than arsenic 3. So yeah, that's what in a nutshell, and that's what we have worked. And these are the groups that I've been working with. I would like, the talk is not complete without, thanking them and saying my gratitude for each one of these groups or each one of these people because they all helped me in my endeavor. So yes, I love to work with them. I still work with some of them. So yeah, it's been a pleasure working with them. And thank you for bearing with me all this while. And really sorry for the technical difficulties in the middle of the ongoing talk. I hope I have mentioned pretty much everything, and I'm gladly waiting for if there's any questions available.
Thank you, Dr. Majumdar, for your enlightened talk. It's quite entertaining and engaging. Could you, sir, remove your slides so that all the participants can
Okay,
see?
yeah, okay.
Yeah, and please try to. I hope this
Okay,
time
so
around.
I have removed my slides. Do you want me to on my camera?
You can minimize it. If they want some question, you can maybe refer it back.
Okay. Like I'll keep it then. Then if they want to question, then I can go to the slide directly.
So would you try to switch on your camera, please? I hope this time around you will be able to do that.
Okay.
Yeah.
Yeah, I hope that.
I think it was some technical thing from our side that was hindering you from switching on the camera. Maybe. So yeah, so all participants, so the floor is open for discussion. And now we can see Dr. Santanu Majumdar. Good to see you back after a long time. So the floor is open for discussion, and if you have any question, one by one, you can unmute your mic and ask our speaker the questions.
There was one question from Anant Kumar. He's asking, what is the simple method of identify of arsenic in water for the villagers?
Sorry, can you say it a bit more loudly? I couldn't hear you.
Okay. He's asking, what is the simple method to identify arsenic in water for the villagers? If villagers wanted to do them by themselves, is there anything they can do?
Okay, yeah, got it. Can I know the name of this person?
Anand Kumar.
Okay, thank you. Okay. Thank you for the question. Yes, so there are various field level techniques available that you can measure on field, which are basically strips, basically color strips. They use colorimetry using different chemicals, and there are different companies. So what you have is, you have a color scale, and you can go to a particular well, you sample the well, and remember, sampling is very important. You cannot just take the water immediately after pumping your well. You have to, purge at least, pump your well for 15 minutes so that you can get rid of the water that was stagnant or standing inside the pipes. And only then you can reach the desired groundwater level that you actually want to measure. So that's important. And after you pump your water enough, you collect your sample. And what they do, you add these different chemicals, and it's commercially available. They call the arsenic field test kits. They're very commercially available. So you add these chemicals, and then your arsenic develops a color. In contact with these chemicals, and by watching this color, there's a strip inside these these containers, and if these strips develop a color, there's a scale in the strips. And just by observing the scale of the strip, you can kind of say the range of arsenic concentration. So it's not a quantitative method, but at least for the field level, you can have a primary idea of how much concentration you have. Say you can have a 10 to 50, or a concentration of below 10. So if it is below 10, you don't really have to collect the sample because that particular well is already safe. So why do you waste your resources by collecting the sample anyway and taking them back for analysis in the lab, which is much expensive? So it's helpful, but that's not quantitative. And there's another one which is called the field spectrophotometer. It's kind of equivalent to the spectrophotometer that I mentioned, kind of object kind of thing. So again, you develop a color using different chemicals, and then you have a field spectrophotometer. By using it, it's simple, you collect, you measure the lambda values, and you measure you use the Lambert-Beer's law, and then you measure the concentration of it. This one is a bit more quantitative than the strips, the field kits, but not that sensitive, as sensitive as the ones in the lab. Okay, I hope I have answered your question. So many people are okay. I see the chats now. Okay, it was not coming in the beginning. Okay, just give me time so that I can go do that. Okay, I see a question for Mr. Swapnil Jaria. Is it safe to shower in water with arsenic? Okay. This question it sounds funny, but when we go to the fields to collect the samples, what the questions we face? We face very, very, many times we face these very questions. That's how, is it good to drink this water? Is it, okay, we can't drink it. Can we cook this, use this water to cook our food? Can we bath? Can we wash our hands? Can we clean our utensils? These are the questions. So I must thank this particular gentleman for asking these questions. Keep in mind, arsenic is only and only threatening once it is inside your body. At the very beginning, I told you that. So until and unless you are consuming arsenic through water, through your foodstuff, be it rice or any other vegetables, because there are a lot of arsenic in your rice, I must tell you, it's not dangerous. And you should not cook, because the cooking soup will ultimately get inside your body as well. You should not drink that water, and you should not eat those foodstuff if you know there is arsenic in those foodstuff, which is very difficult to know. So yeah, you can bath with water. You can wash your hands. You can use wash your clothes. You can wash your utensils. That's not a problem. Okay. I see another question. From Mr. Anand Kumar again, the second one. Is there any instruments available in the market that you can use to remove arsenic? Okay, no. As I told you, there are instruments available in the market, of course, but they are very expensive. There are household instruments, filters. There's a filter called Amal arsenic filter, which you can use. And then there is the methodology that I have mentioned at the household level. These are not instruments, but very, very natural, green way of treating your water at the household level. You can use a lemon, sunlight. What you have to do, you have to fill your water. Just keep a little bit of space at the top of it. 1 liter bottle. But have to have a lot of iron too in your water. That is true. Then you add a few drops of lemon juice, 4 to 5 drops of lemon juice. You put it on top of your roof, inclining by 45 degrees so that your water bottle is completely exposed to the sunlight. And try to use the maximum sunlight. So maybe 10 a.m. in the morning and keep it till 2 p.m. And once you see the precipitates come, country, farmers are using it as much as possible. They're using these submersible pumps to withdraw water from groundwater. They don't understand the chemistry is changing. All they need is water. So somehow the government and the policy making agencies need to think about, keeping a balance that how much you can actually withdraw from beneath the ground. There are developing countries around the globe, but developed countries, they don't allow you to do that. You cannot abstract as many groundwater as possible from you. I mean, you are killing yourself. That's a suicidal thing. It's the only easily available source available. Because treating is aquifer. You have ocean water. Can you treat it? No. Can you treat arsenic? You can't even treat it for salination. There are
Unmuted.
methods going on. But how much is the cost? It's huge cost. It's thousands and thousands of dollars per liter of water filtration. To take care of our bills by charging it using rainwater or whatever. And we have to think about alternative processes like rainwater harvesting or surface water treated. That's a very good question, I must say. And thank you for asking that question. Okay.
Any other questions?
I don't know if anybody, because I'm coming out and half an hour going down.
So Dr. Arunraj বিশ্বাস has asked, is there a sophisticated ACRS surface enhanced Raman spectroscopy method to determine the arsenic in the drinking water using gold nanoparticle as an external analyst? So, Dr. Anurag Biswas, Arunangshu Biswas, sorry, Arunangshu Biswas, apologies for the mistake in the name. So,
I see. If we are determine surface enhanced Raman spectroscopy method to determine the arsenic in drinking water using gold. Not only Raman, I mean, there are laser ablation recipients that you can use, which is even more sensitive than the Raman spectroscopy in terms of measuring arsenic or any other metal ion that nanoparticles. There are something called seams, secondary ion mass spec that you can. But the thing is, again, I mean, these are for very, very analytical or R&D level methods. You know, it's very expensive, very, you need a lot of training, and then, of course, the maintenance and operation is very expensive, but you can do it, yeah. Yeah. I see a question from Mr. Chudasama Hidden R, or maybe Hidden R Chudasama. What is total maximum daily load? Can you tell me, like, in terms of what? Because the daily load in terms of what? In body, or in water, or in total diet? What you are trying to ask me? I don't know if he's here. Okay, so I don't know. Okay, so I don't get the insight. So the TMDL depend, as I said, depend on how much you're consuming. Like how much you're consuming the contaminated water or contaminated food, and how much your body is getting contamination of the the per day diet that you're having. So I don't know. I would have needed a bit more information to answer this question more precisely. I'm sorry if I misunderstood you.
Okay, so
Okay, how can we naturally remove arsenic from body? Mr. Swapni Jharia asking. From body? No. The body by itself, by its own innate immunity can do that to some extent. It's on the dose, the exposure duration. If you are getting exposed for the longer duration with higher concentration of arsenic, not only arsenic, but any other contaminant, for selenium, it's a good thing, but if you have higher amount of selenium, it's bad. For fluoride is very, very essential, but if you have high fluorine in your water, it's bad. So it's about your body can adjust with any other, any foreign body or any contaminant to a certain extent, but after that it can't. The moment the biomethylation process gets hampered or gets indulged by the concentration of arsenic, then the body will collapse. You need to have additional external aid to help your body to do so, and there are certain indirect clinical ways to do so. But the problem is, as I say, the manifestation time is very long, and once you understand that you have
Hello, sir, we are unable to hear you. Yeah, we can't hear you.
Muted.
Dr. Santanu, have you got disconnected? No, I don't know what's happening. Yeah. Okay. Can you disconnect yourself and come back again? Possible. Just leave the meeting. Yeah, please.
Unmuted.
Dr. Majumdar somehow disconnected. He's trying to connect him back into the meeting. So thank you for your patience. Yes. It's 995 870 637. 995 870 637.
All the participants, please don't leave the meeting. We'll take a snapshot after the completion of the seminar. Please wait for a while.
Hello, can you hear me? Can you hear me now?
Yes, sir. I can hear you.
Okay, so I think I've lost a lot of questions. So can you guys help me with some of the questions?
Uh,
If there is any left,
was
do you guys see it?
Archand Rahi. When we calculate contamination factor for arsenic, what is background value and what is base for selecting background value?
Okay, can you repeat that one more time?
When we calculate contamination factor for arsenic, what is background value and what is base for selecting background value?
Okay. I don't know what exactly you asked me because there is no contamination factor as such in terms of geogenic contamination of any kind, being it arsenic, fluoride, or anything. But the thing is that
Okay, again. I am.
yeah, so because the concentration of water is the most important thing. So you have to measure the concentration of water based on the guidelines given by the World Health Organization. The 10 microgram per liter is the background, as you may say. So that's the first thing. And then for solid samples, for example, for rice or for sediment, there are guidelines value as well. You have to know those guidelines value, and those are the basic background factors. So as such, there is no contamination factor that you have to calculate for geogenic contamination. If not like viral outbreak or viral contamination. Yeah. What the Brita filters does it? Okay. Okay. I'm not sure if the Brita filters has been used for arsenic, to develop arsenic filters to a greater extent. I have known there was a group in Sweden who did try that. I don't know if any other group did that, but I know that that group tried that from Uppsala University in Sweden, and they didn't have good results because of some short. They also tried to, combine a kind of a biomembrane alongside the beta membranes, beta filters, and there was some membrane fouling that caused a lot of problems. So I don't know. I mean, I don't know if beta filters had worked for arsenic filtration till date. But if you find any literature, do send me one. I would love to read that because I've not seen one yet. Okay. I'm also trying to find out questions, but oh my goodness.
Yes, sir, I have one question.
Yeah.
So, you said there are like two inorganic arsenic that are dangerous. One is arsenic 3 and arsenic 5. There are two, arsenic 3 and arsenic 5.
No, those two are the most predominant ones. Yeah.
Predominant, but which one is the most dangerous, arsenic 5 or arsenic 3?
Which one is the most toxic, are you asking?
Yeah, most toxic.
Arsenic 3. That's arsenic 3 because of its bioavailability. It's more mobile, it interacts with the biomethylation process much faster. So that's the one. But keep in mind, your system has to be reducing because if it is oxidizing, then obviously arsenic 5 would take charge. But overall, in general, arsenic 3 is the most toxic ones.
Can I ask you one more thing?
Sure.
Which one get dissolved in water at which pH?
Which one gets dissolved in water and?
At what pH of water?
Okay.
Yeah.
Okay, so the natural arsenic is anyways dissolved in water, right? The circumneutral pHs. All these waters are usually circumneutral pH. From 7.5 to 8.5, around that. That's the circumneutral range. However, there are acid-mine drainages. I'm talking about only natural water system, and then we'll come to the synthetic samples that you want to prepare. So for natural, there are acid-mine drainages, and you will have a huge lot of concentration of arsenic, right? And the pH is like below 2 out there, but you still have a lot of arsenic. Why? Because there are microorganisms that helps you through the microbiochemical reactions to keep those arsenic in the system. So that's an extreme environment. That's a different one. But for general natural water systems, it's the circumneutral ranges that the natural arsenic can remain dissolved. Now coming to how do you prepare arsenic 3 or arsenic 5, because that's the most regular one that we work with in the lab. How do you dissolve them? Because you have to use, because there is no elementary arsenic salt or things like that. So you have to use some sort of sodium salt or disodium dihydrogen salts or things like that for both arsenic 3 and arsenic 5, and that's very difficult to dissolve them in water, to be honest. So you have to adjust the pH using different alkalis and acids to in order to remain make them dissolve in pH. But usually for arsenic 3, you have to use a 0.1 normal sodium hydroxide alkaline pH range, which is usually, say, it can vary from 6. How much concentration you want to add. It varies from 6.5 to 7.8 or 8 for arsenic 3. And for arsenic 5, it's pretty easier. You don't need that concentrated sodium, right? So you can use a 0.05 or even 0.01 normal sodium hydroxide, or even a 0.05 normal HCl to keep arsenic 5 in solution. If it's acid, it remains in around, say, 6.5 to 7.7 or sometimes 8. If it is the sodium hydroxide method, then it would remain at around, again, it's 7.5 to 8.5.
I know you said that it is well known that why in your area in Mexico from where you are taking the sample, why the concentration is so high. But since we don't know, can you please explain why you find so much high concentration of arsenic there?
You mean in West Bengal?
Yeah. You said in Mexico also you said you have tried. So
Yeah, so as I showed you in the map, it's not West Bengal in India, or it's not either India and Mexico in the world map as well. Almost 47 countries around the globe are highly contaminated with arsenic in water. If you add food stuff to that, it will go up to as high as like 77 countries around the globe. High concentration of arsenic in rice and wheat and stuff, vegetables, stuff like that. And also milk, cow milk and things like that. But in water, why so it's not only West Bengal. Of course, West Bengal is the most contaminated one, but outside West Bengal, UP is highly contaminated. Chhattisgarh is Bihar, Punjab is highly contaminated. Assam, these are the states with high concentration of arsenic in India. Now, why it is that? Okay, that's a very good question. If you see, all the states I've named, they fall around floodplain, riverine floodplains, So if you see, all these are floodplains of Ganges River. Starting from, and Punjab is of course the river of five plains, the five rivers of Punjab. So if you see Uttar Pradesh, Bihar and all these are actually, these states were created on the base of the watershed, the Ganges watershed area. So these are floodplains. Years and years of organics, mixed with your sediment because of flooding from the rivers. And that's why you see a lot of agricultural, effective agricultural activity in those areas as well. Because you have a very fertile land. For the same reason, you have a lot of organics. So the moment you have the organics, a lot more organics, it will have a reducing environment. Now, minerals are everywhere. The major sources in sediment are the minerals, arsenic-bearing minerals, and they are everywhere. But why is it in these areas? Because of abundant, access to lots and lots of trace organic matter, and that's why you found these high concentration of arsenic in these areas. So diesel organic carbon is good because it helps with agriculture, but it's not that good when it comes to arsenic contamination. So that's the dilemma, double-edged sword, you can talk, say.
Okay, so with this, we will end the question session. I think we have given enough trouble to Dr. Majumdar asking a lot of questions. So now I invite Dr. Chaddi Pathak, who is a faculty member in the Department of Applied Chemistry, as well as one of the important organizers for this event, to give the vote of thanks.
thank you, Soumya. Good evening, all. As all good things come to an end in life, so is the webinar. On behalf of Department of Applied Chemistry, Jabalpur Engineering College, Jabalpur, I take this opportunity to propose vote of thanks to those who have directly or indirectly contributed to this webinar organized by Department of Applied Chemistry. At the outset, I thank our resource person, Dr. Shantanu Majumdar, for inspiring us today with his knowledge and experience. We are thankful to our Honorable Principal, Professor A.K. Sharma, and the Head of the Department of Applied Chemistry, Professor S.K. Srivastava, for their motivation and enthusiastic support. I would like to extend my gratitude to the coordinator of the event, Dr. Souvik Dey, without whom this webinar would have been impossible. And special thanks to the organizing committee, Dr. Rajiv Chandak, TQ Coordinator, Dr. Shailja Shukla, TQ Global Officer, Dr. Anupam Maheshwari, Dr. Shilpa Saxena, Dr. Kanchan Khare, Dr. Vasudha Saxena, Dr. Pratap Reddy, and Dr. Chandani Pathak for their unflinching support and coordination. A heartfelt thanks to all the participants for their active participation in a very interactive session, session. With these warm words and a kind message, we move to the end of today's webinar. Thank you. Stay safe. Now I would like everyone to please open your camera so that we can take a snapshot.
Or we'll take three of us.
Please try, everyone. Please try to open your camera.
Please, everyone.
Please, everyone. Thank you for making today's webinar a very successful webinar. I think Mr. Majumdar would agree with me.
Yeah, absolutely. I would say that it's an honor and privilege. Thank you all. Thank you today. Thank you, your father, for your faculties, for your students out there in the college. It's an honor and privilege to share my with all of you. And I was glad that I received some questions were very, very relevant and very, very important. That was the most thanks for receive those questions. I hope I had answered most of the queries in my limited knowledge. So yeah, I look forward to more such things.